Um, First of all, very good evening, everyone, one and all respected present over here. Hope you all are doing well. So, I'm Dr. Chandni Rani, currently working as an assistant professor, University School of Business, Chandigarh University, India, Mohali. So, I feel truly honored to be welcome to you all to day 4 of our 7-day online workshop on research methodology and econometrics. So at the very outset, I would like to extend my heartfelt thanks to Dr. Firdaus Ahmed for entrusting me with this opportunity to serve as a moderator for this enriching academic journey. So it's privilege to be a part of this STEAM platform that brings together bright minds and curious learners from diverse backgrounds. So today's session marks the beginning of a deep dive into the world of research methodology and econometrics, so which forms the backbone of evidence-based economic research. And our focus for the day is time series econometrics, which is time series econometrics is a specialized branch of econometrics that analyze data collected sequentially over specific intervals, enabling researcher and practitioner to uncover meaningful patterns, trends, and seasonal effect. So in today's workshop, we'll provide deep insight into these methodology, equipping us to effectively handle real world economic forecasting challenges. So with that, it gives me an immense pleasure to introduce our esteemed speaker for today's session, Dr. Dr. Bhagirath Baria is serving as an assistant professor at the Department of Banking and Insurance, Faculty of Commerce, the Maharaja Sayajirao University of Baroda, India. So he teaches quantitative technique, risk management, and related subject at the postgraduate level. So his area of research include applied macroeconomics, including the macroeconomics of banking and agriculture economics, with a strong focus on applied econometrics analysis. He has also published articles in leading Scopus Index and other reputed journal, along with the full-scale book on the economics of financial services in emerging economies. With having contribution from 10 internationally acclaimed experts and also trained student and professional on applied econometrics in India and abroad, and continue to pursue his high quality research with both national and international collaboration in the domain of economics, banking, and international finance. So he has two more books and several Scopus and Web of Science Index forthcoming. So he is also the founder of Cafe Economics, and we are indeed privileged to have his with us today. So please join me in welcoming Dr. Bhagirath Baria for his session on time series econometrics. So thank you, sir. So the floor is all yours.
Thank you so much, madam. And just to confirm, am I clearly audible to everyone?
Yes, sir. It's your voice is audible.
Wonderful. So a very warm evening to all the participants. Definitely sincere thanks to Dr. Malik, OP Jindal University, Professor Hebatala, and other important esteemed members of the fraternity who have organized, conceptualized, and theorized this particular workshop. Uh, Indeed a pleasure to be connecting with you all. And as I see, you all have learned about fundamental econometrics, particularly ending with regression. This is what I hope. And we will take forward that discussion and move to a more sophisticated and a more interesting way of analyzing data. See, in the end, we are all trying to understand data, isn't it? We have some data and we want to analyze it. What kind of data do we have determines what kind of methods are we going to choose, what kind of econometrics are we going to practice. So understanding your data is very important. With that note, let me share my presentation screen, and in a moment it should be visible. Yeah, it should be visible to all of you now, I hope. So Dr. Malik or somebody can quickly confirm if my screen is visible.
Yes, please go ahead.
Yeah, wonderful. So uh, let's start. Let's get into the business now. And the business is very clear. We need to understand time series econometrics. I assume that you all are trying to develop your skills, and I am having the assumption that you all are beginners. If there is an intermediate or perhaps an advanced practitioner amongst you, you will get a kind of refresher, and then we can always interact after the workshop. The broad content is presented here. We'll start with a very fair introduction, simple introduction to what time series data are. We will understand the core concepts that you must know about. Without understanding those concepts, do not start doing time series econometrics. We will look into the classic old age ancient debate of non-stationarity in time series data. It's a headache for everyone. Increasingly, it has become a great source of debate and development of new methods such as co-integration, error correction, etc. We'll also learn how to test for stationarity and what are the major approaches available. And finally, we will end with the workhorse, the foundation or the most fundamental toolkit for forecasting in time series econometrics. That is the ARMA family of models, ARMA, autoregressive and moving average models. So we'll bring all of them together, and then we will end with a demonstration in EViews. I have shared a data set with all of you through Dr. Malik. I'm sure you must be having it. So let's go on the first part. Somebody is unmuted. Please mute yourselves. Do not create disturbance during the session. Somebody has unmuted themselves. Whosoever they are, please mute yourselves.
I request all the participants to kindly mute yourself.
You should mute yourselves, otherwise Dr. Malik will get really angry, and you don't want him to get angry. So you should kindly mute yourselves now. Otherwise, you will be removed, I am sure. So, can the IT team locate who is unmuted and just mute them manually? Yeah, I think they are muted. So great. So we'll start with the first part, introduction to time series data, not econometrics, mind you well, data. What is time series data? So in front of you, I have put a screen, a variable. Those from economics, commerce, accounting, finance would understand the idea of income and consumption. Income is what you earn. Consumption is what you spend on stuff and experiences. If you aggregate all the income of everybody in the country, you have total disposable income. The time series graph or a simple line chart of disposable income and consumption are shown. Naturally, the difference between them is savings. Whatever you spend out of your income, the gap here between the red and the green line, it shows savings. Now, as you see, this data is ordered over time. It starts from 1960 and goes till 2010. It's not very latest data, but you get the point. So it's a data which is naturally ordered in time. Its emergence, its recording, its occurrence is fixed in time. You can't change that ordering. In cross-sectional data, it doesn't matter if I take one cross-section unit before the another, the final analysis will remain the same. But in time series data, the order matters. What has happened in 1960 cannot be put in 2005 or 10. So data which are ordered over time are time series data. As you see, it's a trending variable. It is moving upwards with time. And this is where the curiosity starts. This is where we start looking into what's behind this, what's the story behind this data, why is it moving up. All right, so that's the idea. The traditional time series econometrics was concerned with this, the another graph that is presented to you. The old school of thought, the classical school of thought in time series was concerned and is still concerned with breaking down a time series variable. If you see this chart that I have given you, on the chart you can see the top portion. All right, the top graph. There are 4 charts within this one single big chart. So the top one, observed, is what the actual data is. This is how you got the data. What variable it is, we don't care. It's a variable whose data is given on the top particular panel. Now this data can be broken at least into 3 parts. A trend, which will show its smooth, continuous rise or fall. It can be upward or a downward trend. The second panel in the chart, you can also bring out seasonal fluctuations from it, that is ups and downs which are roughly fixed, or I would say fairly fixed. For example, during festival seasons we see a rise in consumption, we see a rise in sales of gold, we also see increase in bank loans, particularly credit card and personal loans. So those are kind of roughly fixed points. It's not very difficult to forecast it. So even though it may be challenging, but you roughly have an idea. This is the time period when my data will go up, and this is the time period when my data will go down. And then once you remove trend, which is your long run information, something which is happening slowly over time and in a particular direction, and also the seasonal fluctuation, which are regular ups and downs, once you remove them from your actual data, the top panel, the last panel that you see here, random variation, is what is left out. Ideally, we want this randomness to be white noise. We want it to be purely random. When something is purely random, there is no further way you can forecast it. That's the fundamental idea. So the residuals or the random variations play a very critical role in econometrics. Whatever is left out from time series data after removing trend, seasonality, and maybe even cyclical variations, if it is there, whatever is left out should not be something that has any systemic pattern or any kind of well-defined pattern. If there is a pattern in that, that means you are missing out something. So that's the broad idea behind time series data. Earlier, the classical focus was to break actual data into its 3 or 4 components. That is how most of the time series econometrics was done. And now things have changed, as we will discuss. Things have changed drastically now. So very fair introduction. If you don't understand this next 2-3 slides, it is fine, don't worry. But if you do, great for you. If you don't, I will sharing some reading material. You read about it. Walter Enders is the reference that I've used. A tough book to digest, but one of the best books written. So the idea of time series econometrics today is not about decomposing time series data into its parts, such as seasonality, trend, cyclical, random. That is already there. That is well defined. Time series econometrics is now concerned with creating and then estimating stochastic difference equations. The concept of these equations is very simple. If you see this equation in front of you, yt is any variable. Yt can be GDP, for example, gross domestic product of the country, which is a function of a0, which is your intercept term, constant term. It is also a function of its lagged values. So GDP today in 2025 is a function of GDP in 24. You can go as far back as you want, but of course you must have that much data. So let us say GDP today is a function of GDP in the past and GDP 2 years ago. So we are taking 2 lags. This is known as a lag. If you link one variable in today's time period with the same variable or another variable which is from a different time period, from the past, the number of years or periods you go in the past, that many lags are applied. So I am taking 2 lags here, for example. And then that xt, which is written here, that is known as the forcing process. The forcing process is the process by which you give structure to your time series variable. This would include all other factors other than your y. For example, in equation for GDP, okay, in equation for GDP, we will include GDP last year, GDP last to last year, but we will also include factors such as fiscal policy, monetary policy, etc. Other factors, control factors, which you feel are important for GDP, not just its past, but other factors other than GDP that are important for GDP. And then finally, the error term will be included in this xt, which is written here, error term. So the idea behind time series econometrics, modern time series econometrics, is to be able to identify stochastic difference equations. Why we call it stochastic? Because in that xt, which is written here on the equation, you have a random term, error term, which is stochastic, which is random in nature, which is not well defined, which may move in any direction without any strong indication of its probabilities. Okay, which direction will it move? I mean, you don't know about that. So that's the main idea in time series econometrics. You want to estimate these stochastic difference equations, and one there is a theoretical stochastic difference equation, but that you need to make it practical. For a layman, they will not understand what the stochastic difference equation is. They want to see a clear regression equation. that you have already studied by now. So to convert that theoretical stochastic difference equation into a well-defined simple, I would not use the word simple, in a well-defined regression equation, you need to solve the stochastic difference equation. So solving them is a challenge. You can theoretically define it, but you have to create it in the form that it can be estimated using OLS or GLS or FLS or whatever ARMA, VAR, whatever method you want to use. You need to create that theoretical equation, stochastic difference equation, into a manner which can be easily estimated by well-defined methods. So that is known as solution to stochastic difference equation. This is the main heart of time series econometrics. It's fine if you don't get it right now. Those first two slides are not really very important, but you should have some idea of the terminology which is used. So here is a typical regression model. I'm sure you must have seen regression models by now, where YT, let us say it is some variable such as GDP, is a function of X. X can be, let's say, we can have fiscal policy or something else, maybe inflation or maybe monetary policy, or we can take a more simpler example. Yes, Sushma Subha has raised hand. If it is urgent, you can ask, or we can keep it at the end. Sushma
No,
Subha.
we can keep it at the end, sir.
Yeah, great. Thank you. So the idea is y is a variable. It can be any variable if you are from accounting or finance. Let's say financial performance of a company, and xt can be some factor that affects financial performance. Okay, whatever in your theory you may know. So xt means that variable in time period t, current latest time period. Xt minus 1, that is the same variable 1 year ago or 1 month ago or 1 quarter ago or 1 week ago. Whatever the data is, if it is yearly, monthly, quarterly, weekly, whatever the data is. And you can go up to p, that is you can take as many lags as you want, and then et is your error term. Whatever is left out, other than the x that you have included, whatever is left out is the error term. Now, in time series data, we have three very important assumptions that we make. Even though it seems theoretical in nature, theory is the source of knowledge. You cannot just go around using softwares and pressing buttons. You need to understand what you are doing and how can you create a story out of it. So there are three important assumptions when you are using time series regression, when you're dealing with time series data. The first assumption that we have.
12:20 पे आई थी।
Somebody has again unmuted themselves. Please mute yourselves. I like.
मैं मेरी क्लास तो कर ही दी ना।
Please have some manners. It doesn't look good to do all this. Please be careful.
So this is the final warning to all of you. Now I am removing you from the room.
Great,
Please
great.
go ahead.
Good, thank you. So there are three important assumptions you need to make when you're dealing with time series data. First is the realization assumption that every time series observation that you have, okay, so let me go here. Every time series observation that you have here, say disposable income in 1960, disposable income in 1965, this number in 1960, in 1965, in 2010, in 2025, that each number of your time series variable is itself created from a process. So there could have been any number. So the GDP, the disposable income in 1960 is around 2000 billion US dollar here. Okay, 2000, roughly 2000. It could have been 5000, it could have been 1000, it could have been 2150. Any possibility, many possibilities were there. However, it happened to be only 2000. So it was realized. There was a realization in the process and only one value was found out. So each number in time series data, mind you well, is itself a result of a process, stochastic process behind it. So it's like you are trying to estimate regression equation, time series regression from 1960 to 2025, but for each year, there was some regression equation going on which created that number. We don't need to estimate that, but we should know about that. That any number could have come, but a specific number has come. That's the realization assumption. A more advanced assumption that is made is known as the ergodic process assumption or ergodicity assumption. It simply means that if you take time series realizations, that is, you take, let's say, GDP data from 2010 to 2015. That 2010 to 2015 data is a realization. It's not the truth. It could have been anything else. So you need to know the probability distribution. Say, for example, in year 2010, GDP could have been anywhere between 5,000 to 10,000. So each of the numbers were possible. So you would have a probability distribution of that. The average value of that would be the true value. GDP could have been less than that true value or more than that true value. What we assume is once we have that sample data of few years, if we keep increasing the data, if we keep increasing the time period, this small sample, that those numbers from 2010 to 2015, for example, in each year they will go closer and closer to that true value of that distribution, of that process, first assumption, realization, the stochastic process through which each number was created. Okay, even if you don't get it, fine, don't worry. Okay, don't worry, oh, we did not get it, so now we can't understand. It's a little bit stretched discussion, but you should have some fair idea about the words. You can always study about it later. And the last one is stationarity. We all know, I mean, come on, so, time series data has to be stationary in order to be used in OLS or some other estimation methods. Of course, if it is not stationary, you have other options available that you will definitely explore in the next session. So we'll discuss all those things. But there are three main assumptions that are generally made in time series data. If you are not able to understand these three assumptions, don't start dealing with time series data. Spend some time on understanding them. It will make your results analysis really good. All right. Fine. So stochastic difference equations that we saw, they are a way of analyzing time series data. Are they the only way? Are stochastic difference equations the only way to analyze time series data? Which one? This stochastic, this one, where you have a forcing process and your lag terms and error term. Is this the only way? No, there are many other ways. I have given some examples. Time series literature has moved far ahead today, and all of them have their own plus and minus. You can use them depending on the kind of analysis you are doing. But yeah, the stochastic difference equations are the most important way of analyzing time series data. Second topic is the core concepts in time series econometrics. These are some terms or concepts that you should know about. Look at this visual exercise that I have presented you. You have logarithm of real GDP for America. I've used Stock and Watson. If you remember, I shared Stock and Watson book with all of you through Dr. Malik. I hope you got it. Chapter 15 was what I told you to read once before we start this. If you have read it, great. If not, pay extra attention. Okay. So you have GDP data, actual real GDP of United States from 1960 to 2017 on the A column, on the A panel. It is logarithmic. Now, what do we mean by logarithm? We take a common number and we convert all the data as by keeping that common number as base. So if you, let's see, your common number is 10. So 20 would become 10 is to 2. So 2. 30 would become 3. Okay, so 10 is to 10 into 3, that would be 30. And then you can take any base. You can take any base. In econometrics, we take natural log. So we take that number E, if you remember, 2.7828, that is its value. So we take that particular number, constant, it's a constant. So we take that particular constant as our base. So whenever we use the word log, generally that is the base. You may use other logs also, but they have different properties. It's not just about numbers. They have different theoretical properties. So you have logarithm of US GDP. Why did we take log? To suppress excessive variations of volatility. It makes the series a little bit more smoother. But then you look at the second panel. It is the growth rate in GDP. Year on year growth rate in GDP. So from 1960 to 61, it changed by plus 5%. 61 to 62, it changed by, let's say, 3%. Then in this 1970, you can see a negative number below the line, zero line. That means GDP decreased of United States in 1970 and 71, between those 2 years. Both are very different variables. What are you modeling? Is your interest in the top one, which is actual GDP level, or is your interest in the growth rate of GDP level? Theoretically, you should know that when you do time series analysis. Just go on differencing the data, then it becomes stationary, and then you start analyzing, then you say I've analyzed GDP. No, you have not analyzed GDP. If you are differencing the data to make it stationary, then you are analyzing GDP growth rate, which is a different economic variable. For example, profit, level of profit of a company is different than profitability or profit growth of that company. Both are different dynamics. Both may have different equations. Different regression equations be required. So then you can't just jump from growth in profit directly to profit. Both are different. So you need to first know what you want to analyze and then choose the method that is required. This is a feel I want to give you. So the first core concept is here. These are very popular words used in time series econometrics. Lag, that is, you take value of a variable, let's say GDP in 2025, and you say GDP in 2025 is a function of GDP in 2024. So there is one lag because only 1 year backward. Okay, we have gone only 1 year backward in time. If you say GDP in 2025 is a function of GDP in 24 and 23, now there are 2 lags. You have gone 2 year backwards. Similarly, you can go as backwards as you want. Each of that movement on the backward side is a lag. So generally in time series econometrics, whether it's economic, commerce, accounting, financial data, whatever it is, mostly we go up to 1 or 2 lags. Sometimes when we are trying to analyze distributed lag models where we want to go deep in past, then we go for 5, 7, 8, 10 lags. Otherwise, 1 or 2 lags are generally good enough to do good time series econometrics. First difference is simply the change between a variable, that is GDP in 2025 minus GDP in 2024 will give you first difference of GDP. GDP in 2025 minus GDP in 2024 minus GDP in 2023 gives you second difference, 2 difference. So you have subtracted the current value. From current value, you are subtracting 1 year old value, that is first difference. You are subtracting 2 year values, second difference. Okay, so generally we should not go beyond first difference. Rarely we go into second difference. And if you are going to third and fourth difference, then only God can bless you. Okay, so just be careful about it. Why I'm saying that, you will understand as we move forward. We can sometimes take log values and then take first difference of the log. First you make it log. Here you can see the top one screen, panel A. It's a log value. Now you take difference between each year of the log. So you get first difference of log. The beauty of this is, for small changes, it is roughly equal to growth rate in the variable. Okay, unless growth rates are very large or very small, first difference of logarithmic values will be roughly equal to the percentage growth rate, yearly growth rate of that variable, actual data variable, without making it log. So whether if a variable is not logged, it is as it is, you take the growth rate in percentage between 2 years, and then you make that actual variable logarithmic, and then take the difference between those 2 log values. The numbers will roughly be the same. You can treat them as equal. The good thing about logarithmic transformation is you can deal with heteroscedasticity, but generally in time series data, we don't really bother much about heteroscedasticity as much as we bother about autocorrelation or multicollinearity. And percentage is very simple, annual growth rate. So you should know these terms very well. This is the data, actual GDP, okay, actual data that you get from a source, government source or a private source, actual data. Its logarithm value is given in the third column. First is quarter, then is actual GDP, then is logarithm. So here we are taking it as base to natural log. Then the growth rate of GDP, that is, you are simply taking difference between 2017 and 2016 GDP and converting into percentage, that is 1.74%. And then you are the last one is the first lag. Okay, first lag means, see, you see the value 1.74 here, it becomes the value for the next year. So earlier 1.74 was the growth rate for 2016, but now when you take one lag, that 1.74 becomes a variable or a value for 2017. So what you are saying is the growth rate of 1.23, which you see here in 2017, is determined by the growth rate last year, which is 1.74. So you have created a new variable. So when you take log, you are actually lags. Let me use the word correctly, lags. When you use lags, you are creating a new variable out of a given variable. So if I take first lag of any y variable, I am creating a completely new variable, which is y t minus 1, which is first lag of y. And if I take second lag, I am creating another new variable. So that is the kind of things that we do in time series econometrics. Another important concept is autocorrelation. You know correlation. X and Y can be correlated. But what if Y is correlated with its own past? So here, the GDP growth rate, the second last column, growth rate of GDP, 1.74, 1.23, if it is correlated with its first lag, which is given here, the last column. They are same variables, they are coming from the same data, okay, GDP growth rate, but you are taking one lag of it. So what if current GDP values have a correlation with their past GDP values? Then we call it autocorrelation, correlation with itself, autocorrelation. If you calculate variance for it, it is autocovariance. Okay, these are very important terms in time series econometrics. It's very simple. Instead of x and y, you have y and first leg of y, or second leg of y, or third leg of y, whatever it is. Okay, it is up to you how many lags you want to take. Generally, first lag should be more than enough for most of time series models. So GDP from 2010 to 25 is correlated with its one period past. So what happens in 2015, you will have actual GDP, but you will have another variable where 2014 GDP will also be included. So you create a completely new variable, you shift the data one period ahead. So what you are saying is today's GDP is now a function of last year's GDP. If for each year there is a relation and there is a correlation, then we will call it autocorrelation. So instead of x and y, you can calculate simple correlation coefficients between y and its first leg. Then it becomes autocorrelation, and covariance, if it is done in this manner, it becomes autocovariance. Stationarity is a very fundamental assumption and concept. We will study more about it right now. But stationarity essentially means the probability distribution. That is, what do we mean by probability distribution? We measure any probability distribution of any variable by its at least first two moments, mean and variance. Okay, keep that in mind. Probability distribution means you are analyzing a variable with its mean and variance. If the mean and variance are stable over time, they are not changing over time, okay, then we say there is a stationary process. So that process is stable. That process will have what is known as mean reversion. That is, it will always tend to fluctuate somewhere around its mean value. It will go, see, suppose this is the mean value. Suppose this is the mean value. The variable will keep on fluctuating around its mean value. It will go up and down, but it will somehow return back to its mean value. It will stay close to its mean value. If it is a trending variable, or if there are breaks in the data, then it won't remain at its mean. The mean itself will shift over time. So the idea is that behind stationarity is that the mean and variance of a variable should remain the same over the entire period. So I hope you have this, you got this idea. This is a very important set of other concepts which you should know. Stationarity that we discuss, we'll again discuss it in more detail right now. Autocorrelation and partial autocorrelation coefficients. Autocorrelation, you relate a current value of y and to its past value. Similarly, in partial autocorrelation, you control for some factors. So we'll see about it, ACF and PACF. I'll just explain you. We'll be dealing with it in EViews also. So the idea is that PACF, partial autocorrelation coefficient, if you are able to analyze it, you will know what should be your AR, autoregressive order. I will teach you all that right now. What is AR and how to determine its order. And if you see the autocorrelation function, ACF, you can look at the MA, moving average order. So PACF is used for determining the AR order, that is lag, AR1, AR2, AR3. And ACF is used for MA1, determining whether it should be MA1, MA2, MA3, etc. Fine. So AR, MA, and ARMA models are there, which we will discuss in detail. So I won't take them up. We'll also look at unit root and differencing. And trend and seasonality is very common. Long run movement in a variable is trend. Regular fluctuations in data, which you can pinpoint and forecast very easily, are seasonality. Co-integration, I won't discuss much. Maybe the other resource person tomorrow would do it, but it's a wonderful concept. I'll share this few slides. I may not be able to share the whole PPT with you, but I'll share a few important slides, and also I'll be sharing specific reading material for all of you. So you can read that and understand whatever I've discussed here. Fine. So we go on the next topic, non-stationarity in time series data. Okay, what do we mean by non-stationarity? Again, stationarity. What is stationarity? The probability distribution of a variable does not change over time. What do we mean by this? Practically, mean and variance of a variable is constant over time. So what if it is not? If it is not constant, then you have non-stationarity. As simple as that. If it is not constant, you have non-stationarity. Now, what does that mean? If your variable is non-stationary, it will have some trend or some breaks in data. So its mean will not remain stable. And if mean is not stable, the variable will not tend to return back to that value. So what happens is, in non-stationary data, if this was the initial mean value, look at me, if you are able to look at me on my screen where my face is visible, if this is the mean value, if you put a shock in the data, a kind of surprise in the data, it may go on moving explosively upwards or downwards or in any random direction, and it may never come back to its original value or near its original value. So such kind of process is very difficult to model, to forecast, to analyze, because it is having so much of instability and imbalance in it that a small change in it can result into explosive movements. All right. So non-stationary data are data where you can't use a well-defined equation to model it. It will keep moving. The equation itself will keep moving. If you create a regression equation for a non-stationary y variable, you can't really trust on that regression equation. It may be true for first 5 years, then for the next 15 years it may not be true, and something else might be going on. So that is the problem with non-stationary data. A shock will tend to remain forever into the system. In stationary data, if you put a shock, there will be a change, but it will die down, and finally the variable will return to its mean value. So we call this mean reversion. Very important concept in time series econometrics. Mean reversion. Is your data reverting back to mean? If it is not reverting back to mean, how will you be able to analyze it with any equation? Because your mean itself is changing. Its value itself is shifting over time. Of course, you can analyze it. There are models and methods like error correction, vector error correction models, etc. But you can't really do that every time. You may not need to do that. Your focus may be something else, where you want to analyze short run dynamics and not long run dynamics. So why are variables non-stationary? There are two major reasons. Either there is a trend in data or there is a structural break. So if you look at the chart that I have shown you, there are 4 different panels, A, B, C, D. Keep D aside, last one. D does not have any trend. That's very clear. D is not having any trend. It looks like noise. It looks like noise. By noise, what do we mean by noise in statistics or in econometrics, particularly random variations that do not have any proper pattern or structure in it. So it looks like noise. But other 3, A, B, C, there is definitely some pattern in them. If you look at A, there is a slight upward movement, but it is not well defined. You can't really put an upward line or a downward falling line here. It's roughly stable, little bit upward movement. But if you look at B and C, there is definitely a trend in them. But A, B, and C, all 3 are non-stationary. The panel B and C are non-stationary clearly because the mean is changing. There is a trend. So when a variable is moving up, if you take average of any 3 years, okay, and you take moving average for all continuous 3 years, they will keep increasing or decreasing. If there's an upward trend, you take any 3 or 4 years and take average of every 4 years continuously in row. Remove first year, add another year, remove the first year, add another year. Keep doing that. You will see the mean value is shifting over time. Or if it is downward falling, it is shifting downwards over time. So naturally, it is not a stationary process. Why A panel is also not stationary? There is a lot of structural break. There is a lot of structural break, and definitely there is some minor trend in that. So when we have trend, we do not have a stationary variable. 2 kinds of trends are analyzed in time series literature. Deterministic, which is a simple linear trend. A clear straight line can be created and you can see the data moving in that straight line. If you ask me, sir, is it there in this particular graph that you have shown? Panel C, of course, it is not a linear trend. There is a curvature. Okay, there is a exponential decay. But if I take a straight line and put it somewhere in between this, it will be a fair approximation. I will be able to roughly approximate the data. My forecasting accuracy will not be very good, but it will be fairly good. It's fine. All right. But if you take the panel B, okay, dollars per pound, definitely there is a downward falling trend, and you can't put a linear straight line out of it. because there is a break. If you see from 1960 to 1985, there is a different kind of trend. It is very rapidly falling down, but from 1980 to 2017, that it is still downward falling, but it has slowed down. So there is a shift in the trend itself. So the mean value must also have shifted. All right, and then there are stochastic trends. So panel C here is broadly, roughly, it's not correct. I'm wrong. I know that, but theoretically it is fine. Practically, I can fit a linear straight line there and create my analysis fairly well out of it. But on panel B, it may not be possible, because panel B is clearly showing a shift in the trend from 1960 to 1985. There is a quick fall in dollars per pound, rate of dollar per pound. But from 1985 to 2017, that fall is quite slow, and for some years it has actually increased, and then again it has started falling slowly. So this kind of shifts in the trend or data clearly show that it is not stationary. So panel B refers to what we known as call stochastic trend. Panel C can be analyzed with deterministic trend, even though I would definitely use a stochastic trend model there. What do we mean by this? I'll just explain you. So stochastic trend is a trend where you cannot have a fixed trend coefficient. Suppose you run a regression of y variable on a trend variable. You know what is a trend variable? Time variable. So GDP is a function of time, 2010, 11, 12, 13, 14. So as soon as 1 year changes, I can estimate a regression equation, and that beta 0, beta 1 will represent the trend coefficient. If it is positive, there is an upward trend. If it is negative, a downward trend. If it is 0, there is no trend. So if you can have a single trend coefficient, and you can visually, graphically, if you can fix a straight line up or down, clear, clean straight line, and all your data points of GDP data will fall on that line or very much near that straight line, then you have a deterministic trend. Why? Because that trend does not have any abnormal movements. It's a smooth trend. Okay, it's a smooth trend. If you ask me, where is it, sir? At the very beginning that we saw, no, GDP data here. You can see this panel A. It is largely very smooth, going up nicely. Not much variation or not much volatility in its movement. Okay, but when that is not the case, and when your data is not trending smoothly, okay, then you have stochastic trend. The first major model of stochastic trend is a random walk model. A random walk model is like you going on a road. I mean, let's say a person did lot of partying. They partied all night. They are heavily intoxicated, and they are moving on a road, and they'll move around in any random direction. We don't know what will happen. All right, but sometimes they go continuously in one direction and then abruptly change the direction. So the trend may change, but you can never know in which direction. So that is known as stochastic trend. Random walk model is the most basic model of analyzing stochastic trend, where YT, let us say GDP in 2025, is a function of GDP in 2024. Fine, nothing great in this, plus an error term. This error term is what makes this a stochastic trend and not a deterministic trend. If you remove the error term, then you have a deterministic trend. But if you can't do that, then you have a stochastic trend. This UT shows that today's GDP in 25 will be equal to past year's GDP in 24 plus some error term. What is that error? How much will it be? You really don't know. That's where you need to do forecasting and other things. So in a random walk model, the variance will keep growing with time. This random walk model will keep going further away and away from its mean. So the mean will keep shifting, and the mean will shift very volatilely, very wildly. We don't know where it will move. Okay, so there is no mean reversion. There is no stable mean or memory. So in a random walk model, the autocorrelations, that is the relation between each year's value of a variable with its past for each year, between 25, 24, 24, 23, 23, 22, 22, 21, these will, as you go backwards in past, it will take a lot of time for the autocorrelations to reduce. That means it will have a very long memory. What do we mean by this? We'll have a long memory. Very long past GDP could have a lot of impact in today's GDP. And this is very odd, because with time, technology changes, policy changes, things change. So old should become useless and something new should emerge. But that won't happen with a random walk model. It's possible that 20 years ago GDP may also play a very important role in today's GDP. Okay, I'm not saying it happens in GDP. I'm talking about the stochastic trend variable, random walk variable, or a non-stationary variable. A random walk is definitely a stochastic trend. Every random walk model is a stochastic trend. But what if you add a drift term, constant? So now GDP is equal in 2025 is equal to GDP in 2024 plus an error term, which is what you know. We store this here in random walk, but there is also beta zero, a drift term. A drift term that we are adding. This drift term, if it is positive, then you will have a clear upward trend. The data will keep moving up. If the drift term is negative, you will have a clear downward trend. Data will keep moving down, but it will be very volatile. The movement will be very volatile. You look at India's stock market returns, Nifty 50 returns from 2018 to 2025 or 24, during Corona pandemic when it fell down and it came up. If you see that graph, there was a shift in the trend. It fell down for some time, then started rising from 2021 onwards. But the rise has not been smooth. So there is a drift term which is positive in Nifty 50 returns. It is increasing with time, which is positive. So it is increasing with time. But the increase is very volatile around the trend. Sometimes it goes really up, then it comes really down. People get panicked, and then people get very happy. So why is that happening? Because of that drift term. So it's a stochastic trend. It's a random walk, but it has a drift term. Now, what happens with the drift term? You can clearly know the direction. It's an upward moving or a downward falling trend. Still, it is stochastic because randomness will play a very large role. It won't be very smooth journey going up or going down. There will be wild fluctuations in this. All right. So I have given you a pro tip, a very important tip. If a variable that you are analyzing, time series variable, whatever it is from now, commerce, management, finance, sociology, political science, whatever it is, if it is time series variable, if it has a unit root, we will study exactly what is unit root. I will explain you that. Then it will definitely have a stochastic trend. If it is stationary, then it will not have a stochastic trend. So you must understand the concept of stochastic trend very nicely. I'll share some good reading material also with you. Why is this is the problem? Why are we so concerned about stochastic trend? Because first, if you use stochastic trend variable, which is non-stationary, if you use non-stationary variables, you know the problems. Your data would not be able to undertake hypothesis testing, the usual OLS hypothesis testing that you do, T and F statistics, other things. They all will never become normal, even if the sample size increases. They will always remain non-normal, and all these hypothesis tests, they depend on the normal distribution. So your significance of individual regression coefficients, you must have studied that in simple and multiple linear regression models. The individual beta coefficient, their significance, p-values, all those things will become useless. You can't trust them. Why is that so? There's a lot of deep mathematics and things involved, but you should know this practically. Second, spurious regressions. If two variables are having stochastic trend, and let us say one is having a positive drift term, okay, in one variable the beta 0 is positive, in another variable beta 0 is negative, then if you run regression, you might find a negative relation between them. If you regress one variable with positive stochastic trend on another variable with a negative stochastic trend, or vice versa, you'll get a regression coefficient which is negative and highly significant, and you will feel as if wonderful, you have found something great. That's nothing great. It's just spurious regression, nonsense regression. Okay, because there is a strong trend element and a drift element. Both are opposite to each other. Drift, so trend are opposite to each other. So both trends are showing very strong relation. They have a common thing known as a trend. If you remove the trend and then you run this regression, you will see there is absolutely no relation between them. So trends can fool you. Trend or trending data in time series can fool you in believing something which is not really useful. So a very practical question that many researchers will face. As you do time series econometrics, with time you will also face. Suppose your y variable is non-stationary. It is not stationary. It has a stochastic trend. But all your x variables are stationary. x1, x2, howsoever many x you have in your regression equation. And you also include a time variable t to control for the trend. Because we are talking about stochastic trend. There is a trend element. If I use a regressor of x variable, which is itself the time variable, and then other x variables which are all stationary, can I deal with this non-stationary problem? Can I go ahead and start doing my regression analysis? No, you can't do that. Why you can't do that? I've explained this here. The first one is what the main answer is. Even if you include a trend with a non-stationary y variable, it will only take the deterministic part of the trend. a stochastic random part, this one, this U part will never be absorbed by the trend variable. If you include trend as a regressor, as an X variable in your data for a non-stationary Y variable, it will take the deterministic trend, that smooth straight line, that it will control for. But what about the random fluctuation around that smooth straight line? That cannot be controlled for. So you can't do that. You need to convert it into stationary terms. We will see how we do that. The second source of non-stationarity is a structural break. Okay, structural break means your individual regression coefficient. You see the equation given here. Yt is a function of beta 0 plus x1, plus xt, then xt minus 1. So lagged value of x. So GDP is a function of fiscal policy. GDP in 2025 is a function of fiscal policy in 2025 and fiscal policy in 2024. And then there is a error term. Now, what if, see, x is going to change, y is going to change, x and y. If you have 5x and 1y, if you have 2x and 1y, if you have 1x and 1y, all x and y must change over time. Then only they are variables. If they are fixed values, they are constants, you cannot do any regression with them. X and y should change, that is fine. But what about the coefficients, regression coefficients between x and y? The betas, beta 1, beta 2, etc. What if they are also changing over time, or there is a break in them? For few years they are positive, for other years they are negative. What if that is there? If that kind of problem is there in your data, then you have problem of structural break. That will also result into non-stationarity in your data. If you ask me, sir, how do I find it? What does it look like? This panel A roughly shows that, there is a lot of break in the data. This is a from 1960 to 70 is falling, then from 70 to 1985 it has gone up, then from 85 to 2000 it has again fallen down, then from 2000 to 2010 it has gone up, then it has fallen down. So if you are analyzing some variable, okay, which is going through breaks, the regression coefficients of x with that kind of variable might also be changing with time. So what do these beta coefficients show? They show the impact of x on y when controlling for all other factors. But this is time series data. Over time, shifts can occur. So if the beta coefficients themselves are changing over time, then you cannot use a single regression equation, find out your beta 1, beta 2, beta 3, and say that this is the effect of inflation on GDP, this is the effect of fiscal policy on GDP, this is the effect of monetary policy on GDP. That effect itself might be changing over time. It might be having breaks, it might be positive for some years, negative for some years, or constantly going up for throughout the period, or constantly moving down. So those kind of things create breaks in data, and such variables will also be non-stationary. They also create non-stationarity problems. So the question comes, how do I test for non-stationarity? When I know that there is non-stationarity in my variable or in my data, how do I test for it? What's the practical way out? See, a very common way is you look at the graph, just like here, you look at the time series graph, and you will definitely come to know it is not stationary. Which one is stationary out of all these? The fourth one, panel D. Why? Because it is reverting to its mean. The mean is somewhere on that zero line. If you look at this chart, the mean is somewhere on the zero line. So while data is fluctuating around zero, it tends to return to zero. And then there is some change in the economy. Again, it goes up, then it comes down, then it goes down, then it comes up. But it is sticking to its zero. It's like, how do I say from a very simple perspective? It's like your commitment to a brand. If you are using a specific brand of toothpaste or mobile phone, sometimes for some periods you may use that brand a lot, sometimes you may try other brands, but in the end you come back to the same brand. That is how it is. Like between two friends, there might be fights here and there, but then of course they always stand together. They are always together in the end. So true friendship is a stationary variable. There will be fluctuations around your friendship status, but you will remain friends. But in non-stationary variables, your status as friends will change. Maybe you become enemy for some time, again you become very good friends, then you start trying to kill each other. That's what non-stationarity does to data. So how do I test for it? You can look at the chart graph and get a feel of it, but that's not very scientific, isn't it? You look at charts and you know, but what form of non-stationarity? There are different forms of non-stationarity. There are different ways of dealing with them. So how do I know specifically scientifically? How do I know that? And nowadays, if you see, friends, there is a very good trend going on in latest journals, Scopus and Web of Science Index, ABDC listed journals. When you are using econometrics in your paper, they expect you to test for non-stationarity, and not just one, at least two to three tests. Which one they are, I'll show you them. I'll show them right now. They expect you to run non-stationarity test using at least 2 or 3 methods, and from all those 2-3 methods, your results should show same conclusion. Then they trust your further analysis. That is how important non-stationarity is. So you can't just take chart and say there is non-stationarity in data. Non-stationarity can fool you. There might be something else and not non-stationarity, and it might show as non-stationarity. So there are a lot of things involved in this. So in 2 hours, I can't explain you everything, but I can give you a feel of this. So the smart way of dealing with non-stationarity for your research papers, books, articles is to test for non-stationarity using multiple approaches, not just one approach. Otherwise, your results will not be relied upon. In peer-reviewed or in other journals, it may be fine. But in good journals, if you're targeting some really sophisticated journal, they will definitely expect you to test for non-stationarity using 2-3 methods. So now comes the practical question. I have 6-7 such practical questions throughout my presentation. Very practical question. If I ask you what is a unit root, you should have a clear idea of that, because essentially all non-stationarity tests test for unit root. So what is this idiotic unit root and why everybody talks about it? So if you take a y variable and you say that y variable today is a function of y variable 1 year ago. So GDP in 2025 is a function of GDP in 24. GDP in 24 is a function of GDP in 23. GDP in 23 is a function of GDP 22, so on and so forth. So if you take only one lag, GDP today is a function of its past year value, then you can have a regression equation like this, which I have shown you in front of you. So yt is equal to beta 0, which is your constant term, plus beta 1 into yt minus 1, which is your GDP value last year, plus an error term. Now, if this beta 1 coefficient here, this beta 1, if that beta 1 is equal to 1 or quite around 1, say 0.99 or 1.01, 1.02, if it is 1 or very much near 1, we say that this variable GDP or y variable has a unit root. Why is that a problem? Because if there is a unit root, the data will definitely have a trend. If it is positive, high value in the past will create even higher values in the future. So if beta 1 is positive, then GDP in 2024, if it was high, GDP in 25 will be even higher. And then because GDP in 2025 was higher, GDP in 2026 will also be even higher. So your variable will start trending, okay, if it is 1. So we test for that. Is your variable, whichever variable you are testing for non-stationarity, if we create a model where that variable is a function of its 1 year old value or 1 month old value or 1 week old value, whatever frequency of data you are dealing with, is the coefficient beta 1 equal to 1? We are testing for that. If we can reject it, then it means it is not equal to 1 and you are safe. You move ahead and you treat it as a stationary variable. If it is equal to 1, then you need to do some manipulations in the data, in the variable, take its first difference, make it log and then take its first difference, or create growth rate out of it. Do something with it to remove that trend. Okay, do something, because that unit root has to be removed. So this is the idea behind unit root concept. What exactly is a unit root? These are the different methods. Shortly, I'll be showing you in EViews, some of them, not all of them. I've given the null hypothesis also. You should know the null hypothesis of every test very clearly. Otherwise, your interpretation will be wrong. For example, all these tests from first to fourth, Dickey-Fuller, augmented Dickey-Fuller, Phillips-Perron, Dickey-Fuller, generalized least square, all 4 have null hypothesis where they assume that there is a unit root. That is, it is non-stationary. They assume that. and you need to try to reject that null hypothesis. But look at the last one, KPSS. It assumes that your series is stationary. Okay, so in first four, if your test rejects the null hypothesis, it is good for you. Your data, your variable is stationary. If it cannot reject, your variable is non-stationary because the null hypothesis could not be rejected. However, in the fifth one, if you are able to reject the null, then that means your data is non-stationary. So these kind of things happen. So the pro tip that I wanted to give you is, if you are dealing with time series data and you are writing a nice paper for a good journal, at least use the second one, augmented Dickey Fuller, the third one, Phillips Perrin, and the fifth one, KPSS. Use any two from these. Ideally, any one from ADF and Phillips Perrin, and then also KPSS. Why do I say that? What is so special about KPSS or Phillips Perrin or augmented Dickey Fuller? There's a lot of theory behind it. Each of them have certain mathematical, statistical properties, like their probability distributions, the kind of test they do, the amount of statistical power they have. They're different. But from a very practical point of view, we don't need to go in the theory of those things. Use at least any two. From the first four, first three, use any one, and the fifth one. The fourth one is used in very special circumstances. We generally don't use it unless it is warranted. Each of this method has a whole theory behind it, whole set of assumptions and requirements. If I do all that, it will take long time to complete, but I have given you a feel of the different tests, and we will take one or two examples in EViews demonstration also. So these are the major tests. Look at the null hypothesis. For all first four, the null is that there is a unit root, and you need to test that null hypothesis. If you're able to reject it, data, your variable is stationary. If you cannot reject, variable is non-stationary. In KPSS, the null is that it is stationary. So if you cannot reject the null, that means your variable is stationary. Now suppose you use ADF, second one, and you also use the fifth one. In the second one, you are able to reject the null. Okay, and in the fifth one, you are not able to reject the null. That is good for you. That means your variable is definitely stationary, because two different methods with different null hypothesis and different statistical properties have given the same conclusion. However, as you do time series analysis, you will come to know many times ADF or Phillips Perrin test will say that the variable is non-stationary, but KPSS will say it is stationary, or vice versa. ADF and Phillips Perrin will say it is stationary, but KPSS will say no, it is not stationary, it may be non-stationary. So in such cases, you need to inspect the diagram, the graph again, look at any structural breaks, look at any outliers. A lot of things need to be done in such cases. They don't generally occur, they can occur. If they do occur, I'm there, I'll be sharing my contact details at the end. Connect with me, we'll discuss about it, we'll look at the data, it's not a big stuff. Okay. So another practical question. Okay, fine, we are testing that beta 1 should be is equal to 1. That is the main test behind non-stationarity. But what if beta 1 is greater than 1? This beta 1 is greater than 1. So if beta 1 is greater than 1, then if GDP in 2024 was high, GDP in 2025 will be even higher by a much larger proportion, and 2026 it will be even much higher, even by a larger proportion. So there will be exponential changes. It will be explosive non-stationarity. We call it explosive non-stationarity. There are no well-defined tests for testing for explosive non-stationarity. We generally test for unit root. Okay, but where are these kind of explosively non-stationary variables used anywhere? Yes, in theoretical finance, bubble modeling, financial bubbles. Many people talk about financial bubbles being credit bubble in the economy. So in 2008-9 that occurred in USA, it burst and recession occurred. So in that when you do econometric modeling for those kinds of bubble, you want to forecast when the bubble will burst, when will the bubble squeeze, then you need such explosively non-stationary data in those kind of situations. Otherwise, we rarely do it in economics, commerce, management, finance, accounting, banking. We generally don't, we would never deal with explosive non-stationarity, because such variables are madly unstable. And GDP or financial performance of a company or accounting ratios, those of my friends who are from accounting field, various important accounting ratios, they have some stable path. They can't go on explosively high or explosively low forever. That's not going to happen, because the regulator will come in the picture, the company will try to control it. There are a lot of people, factors trying to control that variable. Here we are talking about a variable which is just madly out of control. I mean, it's just out of the sky. You can't even understand how high or low it can go. So yeah, so we come on our the final part. This is the most challenging part, but it's so simple. If you pay a little bit attention, you'll be able to understand it well. These are known as ARMA models, and there is a whole family of ARMA models that I've shown you here, which I'm going to explain to you one by one. So AR models, MA models, ARMA models, ARIMA models, where you have a new factor called I, then ARMAX, and then finally we will look at ARIMAX models. What are these models for? They take a time series variable, whatever variable you're dealing with. Let's say if you are a researcher in the field of accounting, management, and finance or commerce, you might be dealing with financial performance of firms. You might be dealing with NPAs of banks. You might be dealing with the profitability of a firm. You might be dealing with, let's say, assets or liabilities of a firm, or the balance sheet ratios or profit and loss ratios of a firm over time, or of an industry, or of the whole sector. Now, if you want to forecast it, you want to analyze it and forecast it for next 2 years, 3 years, 5 years, or if it's monthly data for next 12 months, 24 months, if it is quarterly data for next 3 quarters, 5 quarters, 8 quarters. How do you do that? The first starting point is to learn ARMA models. And you should always try to use ARMA models unless and otherwise they are not suitable. I mean, you are not able to find any logic behind them, then only you should move to more advanced models like VAR or structural VARs or ECM, VECMs. Don't just jump to them unless it's really necessary. So the background to ARMA modeling is the Box and Jenkins method. Two professors, Professor Box and Professor Jenkins, wrote a wonderful book in 1970, very old book. And that book changed how we look at time series data. I told you earlier that time series data was only concerned with decomposing the data into trend, seasonal variation, and random variation. That was the original use or focus of time series analysis. Statisticians were playing a much bigger role at that time. No, statisticians are different, econometricians are different. You should know that. Just because you do statistics does not mean you are doing econometrics, and vice versa. So proper time series econometrics can be traced to Box and Jenkins' book. So they developed this ARIMA, or popularly ARMA modeling. They created a framework for ARMA modeling. They said that if you want to forecast a variable, you can do ARMA, but you can do ARMA modeling using our method. And the method is quite simple. There are 3 steps in this. In the first step, to identify your Y variable and X variable. Okay, I'll show you the next slide. Look at this equation. Let me explain you the equation first, okay, so that you don't get confused. The equation is very simple. It says Y, which is now a star variable. What do we mean by star? It's a stationary variable. So you need to have a stationary variable here. So Y, let us say let me take a simpler example. The salary in a firm from HR, human resource management perspective, the salary, average salary in a firm of employees at certain level, let's say mid-level management, is a function of the salary last year. So this year's salary is a function of salary last year, salary in the last year, so on and so forth, plus an error term. So this is very clear. This kind of structure is known as autoregressive structure. Why we call it autoregressive? Because you are regressing a variable Y on its past. So you are not regressing Y on X or A or B or C, something else. You are regressing it, creating a regression equation where on one side, that is on the right hand side of the equation, you have on the left hand side of the equation you have a Y variable, but then on the right hand side of the equation you again have Y variable but lag values of that Y variable. So we call it auto-regression, regressing a variable with itself. Autocorrelation, correlating a variable with its own past values. Auto-regression, regressing a variable with its own past. And then you have an error term. So forget about other things. Till this ET, till this point ET, what you have is an autoregressive model. Autoregressives have an order. First order means you have only one flag value. So GDP today is a function of GDP last year. But autoregressive 2, AR2 means GDP today is a function of GDP last year as well as last to last year plus an error. So that is known as autoregressive model. A more unique model is here in the second half on the right hand side, where you have error term. So now your Y variable GDP is not only related to its past, but also to the past errors. Okay, also to the past errors. So in 2024, actual GDP was something, but your regression equation, which you created here, would have estimated some other value. It will never be perfect. No regression can give you 100% perfect value. That is impossible. Some randomness will always be there, which you cannot measure. So actual GDP and the forecasted GDP using your ARMA model here would have a difference. That difference is the error term. So today's GDP is a function of last year's GDP plus the error that was committed last year. So in 2025, GDP in 2025 is a function of GDP in 2024, AR1 model, autoregressive 1 model, because you are taking GDP and its 1 year old value, or if it's monthly data, then 1 month old value. But now you have another variable, past year's error. Now what is past year error? In 2024, you had actual GDP data, which was given by the government of India, but you also had GDP data based on your own actual model, which you have created here, some forecasted value. And there was a gap between actual GDP in 2024 and the forecasted value. That gap last year, that happened last year, is now included in this year's GDP equation also. So let us say the profit of a company, of a manufacturing company in 2025 is a function of, is dependent on its profit in 2024 plus the error that was made in forecasting the profit. Why there was an error in 2024? Because in 2024 your equation gave you some number, but your regression equation also must have given you some number, predicted number, and both had a gap. So that error of last year also becomes a factor this year. So this is from where generally the idea of error correction starts. We learn from our error. We as individuals, companies, governments, countries, everybody learn from their error. So what we are saying is today's variable is a function of its past, but also the error made in the past. And naturally, you would learn from your error. Otherwise, you are idiot. You are a dumb person. I mean, a rational person learns from their mistake. So if I did a mistake in investing money in a share, and this year I chose a share, how did I choose it? Depending on the returns last year. But this year I also chose the share and invested amount of money in that share depending on how much error I made last year. So that's an MA component, moving average component. So here in moving average models, we take into account the error term. So this year's GDP is a function of this year's error. That is fine. What is this error? If you take all this Y, AR terms, autoregressive terms, if you remove all of them, whatever is left out in current GDP is error, but we are also including past error here. All right. So you are learning from your error. It's error learning model here. How deep in the past can you go? If you go 1 year in past for errors, if you take this year error as well as last year error, then there's a MA1 model, moving average 1 model. If you take this year's error, last year error, last to last year error, it is MA2 model, so on and so forth. So I hope you got the idea of basic idea behind AR and MA models. In AR models, you do regression of a variable with its own past. In MA models, you do a regression of a variable with the error in the past in forecasting that variable. All right. So this is known as AR and MA models. If you combine them into one single equation, like I have done here, you have ARMA models. So what does the Box-Jenkins method say? It simply says, first, you find out what are your Y and X. Now, how do you know what are your Y and X? Theory. The theory that you are analyzing in the literature review. That will explain you what your Y and X should be. Which one should be X, which one should be Y. Then you identify, now here we are not talking about X. Okay, in ARMA modeling, if you only include Y and forget about any other variable, it's ARMA, ARMA. or ARIMA. I'll show you what's the difference. But if you include an X variable, new variable other than Y, then it becomes ARMAX, ARMAX or ARIMAX. That X shows some other factors, control factors, which are different than the Y variable. So what's the idea behind ARMA modeling? You don't look into any X, only use Y and its past to predict and forecast its future. You don't worry about any other variable. GDP can be forecasted simply using its past data and past errors. If you use only past values, AR model. If you use only past errors, MA model. If you use both past values as well as past errors, ARMA models, ARM. So Box-Jenkins say, first you identify the Y and X. The P here, the first P is the order for the ARMA, for the AR model. So it should be AR1. So you want to go one, you have to want to have 1 lakh 1 year in past, or you want to link today's GDP with 2 years in past. If it is 2 years, then AR2. So the value of P will become 2. Then last one, Q. Forget the D1. Last one, Q, is the MA order, moving average order. Are you taking only last year's error along with this year error? This year error has to be there, plus last year error. Or you are taking last 2 years error. If it is last 2 years error, MA2. If it is only last 1 year error, MA1. Generally, in most of your accounting, finance, banking, commerce, economics related applications, 1 or 2 lakhs will be more than enough. Beyond that, moving beyond that will take you in a very different kind of analysis. Mostly it should be enough. You have to be smart. You can go very deep in past and increase your R square and other things, but then it will cost you statistically. All right. The first step is to find out YX. Sorry, forget the X. We are not dealing with RMAX or ARIMAX. But if you include X, it becomes RMAX or ARIMAX. Some other variables other than Y. The idea behind ARMA modeling is not to use anything other than the Y variable itself. The second step in this is, now that you know the order of your AR and MA, that is, let us say you are having AR1 and MA1, which is the most popular model. So what does AR1 mean? GDP today is a function of GDP last year, so AR1, and MA1 means GDP today is a function of the error committed last year. So that's MA1. So you identify P and Q. How do you do that? We'll see that practically in some time. Then second is, now you need to estimate the coefficients. If you look at this screen that I have put in front of you, you can, if you look at the screen, there are a lot of coefficients here. It's theta1, theta2, then up to theta p. There are so many coefficients. You need to estimate them. You need to estimate them. Generally, you do that because the variable Y variable is stationary. You have to make it stationary before using ARMA. So you can use OLS approximations. You can run OLS. There will be approximation of the underlying maximum likelihood estimator. What does it mean? Don't get into it, but you can use OLS in that if your variables are stationary and invertible. So what is this invertible now? Till now we were talking about stationarity. Where did invertibility come? Stationarity takes care of the AR model. What about the MA model? MA is also there, moving average. Just like stationarity in AR, you need to have invertibility in MA. I'll shortly explain you what it means. So for second step is estimate the regression coefficients, and then you check for diagnostics, autocorrelation, multicollinearity, etc. I'll show you that in EViews shortly. You do that. This is the broad idea of Box-Jenkins from Walter Enders. Wonderful book. Let me have some water. Wonderful book, I must say, but very dense and demanding. That is why Stock and Watson is much better. I shared that book with all of you. Read the chapter 15 of Stock and Watson, very good. And also read Damodar Gujarati's chapter 16 or 17 on dynamic econometric model. There also they talk about time series model. That's also a wonderful book. But Stock and Watson is by far the best introduction to time series I've seen. Introduction. So this is the idea behind Box and Jenkins. In identification stage, you find out the P and Q. You look at the missing values. Look at the graph of your Y variable, your Y variable, which you are going to analyze through ARMA. You see whether there are any extreme numbers or data, abnormal fluctuations in the data. All those things are to be done at this stage. How do you know the P and Q? This is a question. So how do we know the P and Q? That is whether it should be AR1, MA1, AR2, MA1, or it should be AR1, MA2. How do I know that 1 and 2? Generally, you use the autocorrelation function and the partial autocorrelation function. How do you practically use it? give me a little bit time. We'll be starting with the EViews demonstration shortly. But this is what you should know. Then in estimation, you estimate the parameters, those regression coefficients, and then you do diagnostics. You must have studied about heteroscedasticity, multicollinearity. You need to do all that here also. Not heteroscedasticity much per se, but autocorrelation definitely, multicollinearity definitely, because you are linking same variable with its past, so there might be multicollinearity in this. If that is there, then you need to make adjustments in your data. So what is stationarity? You know, when variable is stationary, AR model is usable. You can go ahead and use AR model, but that is stationarity is not sufficient for MA model. For MA part, you need to have an invertible series. I'll not get into detail of this, but you read about it. What is invertibility? By invertibility, we mean that this coefficient, the coefficient between YT and its past error, the past error, immediate last year's error, that should be less than 1. So in stationarity, what we say, the unit root, we should not have a unit root. It should be less than 1. The AR1 coefficient should not be equal to 1. It should be less than 1. Then it is stationary. So for MA component, the first order MA coefficient should be less than 1. Then it is invertible. If both are fulfilled, then only you can go for ARMA model. Now, why do we need lags? Why are we talking about lag, first lag and second lag? Why don't forget about lags and simply use current values and link all current values and just go around doing analysis? There are several reasons. Damodar Gujarati explains them very well. There are psychological reasons where people take time to learn. Error correction, error learning models are there. People learn from their errors. So you can't ignore lags. There are technological lags. Sometimes changes occur in one variable, but they occur because something else changed 2 or 3 years ago or 5 years ago. So technology has a slow impact on economy. So if you take GDP as Y and you take technology as X, you can't take current technology and current GDP. You need to allow some lag in adoption of that technology in the economy. Such lags are there. That is why we need lags. This is an AR model, first order autoregressive model. YT, whatever your Y variable, whichever field you are working in, YT is a function of beta 0, the constant term, plus its last year's past value, plus an error term. This beta 1, it shows the AR1 coefficient. Why this is AR1? Because only last year's value is included. You can go up to P, AR2, AR3, AR4. Generally beyond AR1 or 2 for yearly data doesn't make sense. In quarterly data, we go up to AR4. Monthly data, accordingly, we go up to AR10, 12. You can go. You may not go. It depends on the data. Really, you can't. There is no fixed menu for this. A distributed lag model is very unique. In autoregressive ADL models, you have AR model, you know, Y is a function of YT minus 1, T minus 2, GDP 25 is function of 24, 23. But also, you look at some other X variables, one X variable, let's say. So along with GDP, you take technology. So today's GDP is a function of last year's technology, last to last year technology, last to last year technology. So now you have two kinds of lag schemes. One is lag of Y in your regression equation on the right hand side, and also the lag of another new variable, your X. So then we call it autoregressive distributed lag model. So GDP is a function of its past as well as the past values of technology. Then it becomes an autoregressive distributed lag model. Why this distributed lag? Because now you have that X variable also coming into the picture. This is also a very popular model. I'll skip this, a little bit technical and theoretically demanding. But these are moving average models. Now you understand what moving average are. You link in this is the ARMA model, but if you remove the portion till sigma et, everything before et, in this equation, everything before this et on the left hand side of et, if you remove all that, you are left out along with et, you keep et but remove everything on the left hand side of et, then you have a moving average model. So GDP in 2025 is a function of error in 2024, error in 2023 in forecasting the GDP. That is what we mean here. So if, see, ideally we want these MA coefficients. If it is MA1, that and then MA1 regression coefficient. Here theta 1, this one. We want these coefficients to be to decay faster. Okay, we don't want them to decay longer. So if you go very leap in past, you say MA1, MA2, MA3, MA4, MA5, MA6, you take 6-7 years past errors into your this year's GDP equation, You want them to quickly, it might be high initially, but then quickly fall down as you go deep in past. But if they are not falling down, if they are slowly reducing as you go in past, that means past has lot of effect on your current values. So then there is a long memory in your data. But if it is falling down quickly, there is a short memory. Sorry, I'm having tea along with this. I need it for my throat. But why do we worry about this? Short memory models are different, long memory models are different. You can use, it's a great thing if you have these kind of things with you, short memory or long memory model. It's a great thing. You can use even more challenging methods and unique econometric approaches. The most important thing, friends, the last thing to know is that if you don't have a moving average specification, you can't create impulse response functions. I will show you how to create impulse responses in EViews, in ARMA models. You can't create impulse responses. Impulse responses are your mini experiments. You know, people in physics and chemistry do experiments in labs. We can do those experiments in impulse response functions. If we change this error term, this ET, current ET, forget about the other ET, we can't change them. They are already given. They are passed, so they are already fixed. Current ET, if we change this current ET value by 1 standard deviation, 1 unit, what will happen to Y? Over time, from first year till let's say next 10 years or 5 years, what will happen to Y? What will be the path of Y? You can analyze those things using impulse responses only when you have an MA structure. You need an MA structure for that, moving average structure. You need to link current value of your variable, Y variable, with its past errors. Otherwise, deriving that will become very difficult. So finally, what is the integrated? Simply speaking, if your Y variable is stationary as it is in raw data form, you say it is I0. So it is stationary as it is. You don't need to make any manipulations. But GDP, for example, or the tax, total amount of tax, GST paid by a firm for the last 10 years, any big firm in the last 10 years, it won't be stationary. It might have increased with time because its scale is increasing, inflation is increasing, economy is increasing, you know, so GST must have increased. So then you need, then you need to difference it at least once. So suppose you difference, you know what is differencing, okay? You take current value of GDP minus its previous value, first difference. Current value of GDP minus previous value minus previous to previous value, second difference. So if you difference GDP data or any Y variable data once, we call it I1 variable. That is, it becomes stationary after first differencing. If it is I2, it becomes stationary after second differencing. So if your data is not I0, which generally will not be, you will have to use ARMA model. So ARMA and ARMA are only differentiated by the difference, the only difference between them, or they are differentiated by the fact that in ARMA we assume Y is I0. In ARMA we accept that Y may not be I0, it may be I1. Ideally it should be I1. If it goes up to I2, still may be fine, but then beyond that it is useless. You need to go for co-integration or something. Fine. So this is the idea. Okay, what if there is, see, we have one Y and many, we can have one Y and one X, or we can have one Y and 2, 3X. All of them can be adjusted into ARMA. In ARMA or ARIMA, let's call it now ARIMA. Okay, I0 is rare in commerce, management, finance, banking. It's rare. So let's call it ARIMA. In ARIMA, if you have, you can have one Y, and from that Y only you can create other X, like Y t minus 1, t minus 2, or you can have additional X variable. Then it becomes ARIMAX. ARIMA X ARIMAX. X is that control factors, exogenous factors that you are including. But in all these cases, Y variable is only one. What if you have multiple Y variables? Then you can have multiple ARIMA equations. So you have Y1, Y2, Y3. For each Y, say GDP is one Y, inflation, unemployment, 3 different variables. Each of them can have their own ARIMA equations, and each of them can become X factor, X variable in other equation. Now, when you have that kind of structure, you don't have equations. Now you have vectors. There are vectors of coefficients. Earlier, you are only estimating individual coefficients. Now you have vectors of coefficients. Okay. So in this case, you need to use multivariate time series models, such as simultaneous equation models. Very tough to do, but all these 3 Y ARIMA, 3 ARIMAs are there. All these 3 ARIMAs can be solved together simultaneously, or you can use recursive structure. Like recursive bar, you solve one and then use its value for the next, then solve it, then use it for the next, and you forecast values like this. Or you can use block recursive models where each ARMA, okay, y1 can have multiple ARMA equations which are solved simultaneously, but then there is a next block y2. There are many equations there also, ARMA equations. You solve them simultaneously, but from block to block you solve it recursively. So block 1 is solved simultaneously, then those values are plugged or used for block 2, it is solved simultaneously. Now those values are put in block 3, it is solved simultaneously. Finally you will have final regression coefficients. So VAR is an extension of ARMA, where it's a multivariate ARMA model, vector autoregressions. So is the Box-Jenkins method the only method to do ARMA modeling? No, many methods have developed since then. While it was an original method, many things have developed. I have given you some examples of this, how beautiful the time series literature is. And no need to worry about this. Stick with Box-Jenkins, stick with the 3-stage process, keep your data neat and clean, do the modeling properly, check diagnostics, create impulse responses. You are fine. You have wonderful analysis with you. Other models, other frameworks, methodologies that I have shown here are used only when there are some specific reasons or very specific conditions in your data. All right. So yeah, with this, I think our discussion of the foundations are over. We can move on to our EViews exercise. And before we go on to EViews, if there are any 2-3 main questions, theoretical questions that you have, I already included a lot of practical questions. If you see, I have at different places included this kind of slides, practical questions. So my hope was that you might get these questions in your mind. But if there are any questions specifically related to whatever we have discussed so far, see, if you are having a research problem, if you are dealing with time series data and you are facing some problem, you contact me personally. We cannot discuss that in short notice here. I also need to see your problem, see your data, read something about it, then I can speak to you. Time series is a very tricky business. Time series is very tricky. So, but if you have any specific question on whatever we have discussed, something that you were not able to get, or somewhere if you have some confusion, you can quickly 2-3 minutes we can give to 1 or 2 such questions, 2 or 3 such questions. So anybody, the moderator can perhaps take up and ask if anybody wants to. Yes, Sushma Subha has raised hand. You had raised it earlier also. Madam, please unmute yourselves and explain.
Achha, sir, I have just one basic question. So, whenever we are talking about these trends, some topics like when we talk about like trends and patterns of poverty or trends and patterns of employment in India. So, by trend, do we actually mean the direction of that particular variable, be it poverty, be it employment? Are we talking about the direction of it, like of that particular variable,
Yes,
it's
yes, very
increasing or
correct.
decreasing?
Yeah, you got the point. The direction of a variable over time is its trend. If the direction is positive, we say positive trend. If the direction is negative, we say negative trend. If there is no direction, it is just hovering around some value, going up and down around it, then we say there is no trend. So you are correct. So if you
And
take actual
yeah,
poverty data, it will be falling over time. But if you take the growth change in poverty, how much is it changing? That also that would be increasing over time. So with every successive year, government is able to reduce poverty by much and much larger extent. So both of them can have different trends. Yeah.
okay. And then second question is that, so what do you mean by then pattern of poverty, or if one is direction, if by trend I mean the direction, whether it is increasing, decreasing, or it's stagnant at one over a particular period of time. When we talk about patterns, then how
Yeah.
do we
Both are
understand it?
different.
How do I? Hmm.
Both are different. Pattern is generally a cross section idea. So when we say pattern, we look at how poverty is across a region, across group of people, across different socio-economic hierarchy. You're talking about space when talking about pattern. But when you're talking about trend, you're talking about time. So if poverty is increasing or decreasing over time, it's trend. But if poverty is very high in, let's say, certain states of the country, but low in certain other states, then we say there's a pattern of poverty in India. So pattern is cross-sectional, poverty is temporal or time series. Direction is time series in nature. So in
Okay.
both the cases, different kinds of data are needed. For pattern, you need to use panel or cross-sectional data, and in
Mm-hmm.
trend, you need to use time series data.
Right. Okay. Okay. I used to get the thing. I'm getting it cross verified with you. So when we talk about the employment pattern among a group of so socio-economic groups like SC, ST
Correct.
or general, so
Correct.
that's
Correct.
more of a pattern.
Correct.
Okay. Okay. And so what was that slide that you skipped? Actually, what was the name of that thing?
So there were
Uh,
properties of OLS estimator for time series data.
oh, okay. Right. Thank you,
I'll
sir.
take next question. Thank you, Mr. Anjali has raised hand. Please ask last question for right now. Then we'll move on to EViews. Then again we'll have question answer.
Hello,
Anjali.
sir.
Yeah.
Sir, actually, I have a research question.
Hmm.
Uh, I want to ask, can we have huge differences if we are using logarithmic changes and percentage changes?
Hmm.
Is it possible that we would have huge differences?
Very nice question, actually, Anjali.
Sir, I'm working on green total factor productivity.
Mhm.
So I have to use like growth rate of various factors of production like
Mhm.
labor, capital, natural resources. And I also use pollutants, different emissions that we have. So I've used logarithmic changes, but I'm not getting significant results. And one of the OECD working paper, they suggested to use discrete changes.
No.
So I
Discrete
haven't
changes will
heard
simply
about.
be absolute changes. Discrete changes will simply be first differences.
Okay, so
It
they
is
would
more
be
simple.
first differences.
Broadly first differences. I'll see. You can share that paper with me later on. Let me see what their argument is. But discrete changes are generally your first differences. Simply the value of green total factor productivity this year minus its past value. Don't make it.
Okay,
Don't
sir.
normalize it. See this difference between log difference and growth rate. Have you tested this analysis with growth rates also instead of log differences?
Sir, I haven't tested it yet.
You must do it. You must do it. See, this is how time series is lot about subjective trial and errors. So do it with growth rates also. If then that case also the results don't change, then you get back to me. We will have to think of some other mechanism. Maybe your econometric model maybe incorrect, or maybe your definition of green total factor productivity, your measurement. There might be some measurement issue in that. So if you
Okay, sir.
so that we need to discuss.
Okay, sir. Thank you, sir.
Right, Sujata Kumari, last question. Now then we have to go to EViews. Yeah, Sujata Kumari, please ask. Sujata Kumari.
Can I use this ARMA model for census stock market
Stock market
time series data? I want to
stock
ask.
market time series data.
Ji.
Stock market time series data. I am not very sure because stock market data. If you take returns, for example, stock market returns, for example, there is a lot of literature that is developed which is far beyond ARMA model. But yeah, ARMA models are the backbone.
Okay.
You can definitely use ARMA, but you will have to use ARMA, not just AR model. You will have to use ARMA both together. Then you
Okay.
can perhaps create a nice model of stock market returns. But then you get back to me what exactly you are trying to
Okay.
measure. I need to understand the main variable that you are dealing with, the source of the data and everything. But yeah, you can use with time series data.
Actually, sir,
You can use it.
my data actually BSc census and its indices like BSc bank,
Yeah, so see, you
BSc
can't use those
real
indexes directly.
estate.
See, if you want to
This type.
see, if you want to analyze
Ji.
and forecast BSc index such as Sensex specifically, the level of Sensex, then you cannot go for
Oh,
first differences and make them stationary. Then you should go for more non-stationary models like co-integration or error correction models. But if you are fine with manipulating them, that is making them stationary, then you will be differencing them or creating growth rates out of them. Then you can go for ARMA models. So first you clarify what you want to forecast and analyze, BSc Sensex level or the change or growth rate returns that it is giving. So you have to first clarify that if it is level of BSc Sensex index that you are trying to analyze, perhaps go for co-integration, vector error correction models. Those will be better. But if you are trying to analyze rate of return in BSc Sensex or other indices, then ARMA models can be really helpful there, definitely.
sir. Okay, sir. Thank you, sir. I'm
Yeah.
trying to
So,
analyze returns actually.
yeah, return. So then ARMA
Returns of
models.
indices.
Then you can start with ARMA models. You can also go for VARs, and then you can go for structural VARs also. ARMA, VAR, and structural VAR. Three are very good
Okay, sir.
options that you have. Even more other sophisticated options are there. You get back to me, but these three are very good options that you have. Definitely.
Okay,
Start
sir.
with ARMA. Don't directly
Thank
go to.
you, sir.
Yeah. All right, so we'll stop the
Okay.
question thing now. We'll move on to EViews, everyone. And I was told that you already have used EViews. I use EViews 8. You can mute yourself, everyone, those who have asked questions. So I will use EViews 8. I shared a file with the organizers, but they told me that it's already there with you. You might be having some latest version of EViews 9, 10, 11. I don't know. I'll be using EViews 8. So broadly, the things are same. So let's go on to our EViews session now. And for that, what I will do is I've shared a data file with you. If you can run the things with me, great. If you can't do that, just have a look at it. The session is being recorded. It will be shared with you later on. You can again go through and practice it. So let us now move to EViews, and let me share the screen of EViews that I have already opened. Yeah. So this is my simple old EViews 8 that I have kept in front of you. And I'll import the Excel file in this. Sometimes, Excel, when you're importing Excel files, EViews create some trouble for you. Like NA shown, error, and all those things occur. So maybe you shut down EViews and start it again. Generally, it would happen after that. Still, if it doesn't happen, then you need to check your data in Excel. If it is numerical or if it's character. But generally, if you close down EViews and restart it and then do it, generally the problem gets solved. So I'm uploading that data that I have already shared with all of you. I hope it was shared to you. And that data is basically from my book with Routledge that I published. So it's just one snapshot of the data. That book has a lot of data in it. So this is one snapshot of data. I analyzed the performance of I have analyzed the output measurement in banking and insurance industry. It's a very big debate. How do we measure output of banking and insurance firms, industry, and the sector? So that is what I have analyzed in there. This is data of output, labor, and capital. There are if you see the variables here, I have I'll open the main variables, the output variable first, then I click on labor, and then I click on capital. I right click them and open them as a group. Now the variables that you are having, if you see the Excel sheet, I have also given another sheet where I have defined the variables, what the definition is, what is the measurement unit, everything I've given you. You can have a look at it there. So the data that we have in front of us is data of India's banking sector. Output shows what it has produced. I have measured output here in the form of loans. It can be also in the form of deposits. There are different schools of thoughts, or an index of both. I have taken loans here. So banks are producing loans. The main work of banks is to produce loans. What do they use to produce loans? The first thing people say is deposits, but there are different approaches in the literature. I have tested all the approaches in that exhaustive book. But here I have used labor and capital, simple production function. Any company, any firm, bank is also a company under the Indian Companies Act. A commercial bank is a company. If any company produces an output, but uses some inputs to create that output. So those inputs are labor and capital here. What is labor? Number of employees in the banking sector. And capital here I have measured in the form of, I'm not sure, there's a lot of data I have used there. Maybe in terms of number of branches of all the scheduled commercial banks in the country. So that's the fixed capital that the banks use to generate their reach to the customers and provide various services. In the era of digital banking, I also use digital banking inputs also, but I have not taken a very complex data. It's a very simple data set. Output of the banking sector, which is produced using labor, that is employees, and capital, the branches. So banks use branches and the employees in the branches and outside the branches, combine them, and then they create loans for the customers. That's the idea behind this. Okay. Now in EViews, you have a lot of options. Okay. In EViews, generally when you have time series data, the first thing that you would do is to go for graphs, isn't it? You just want to take a feel of the graph. So we have the option on the top left side, view, and then we go to the option graph. Once you click on the option graph, it will open another screen. It is loading in my case. I don't know if it is visible to you or not. Yeah, it is visible to you. So there we take the line and symbol graph. This is the beauty of EViews. You can take raw data, you can take the means in the data, you can take only the last observations, first observations, you can take the sums of the data, but we always look at raw data. The first step in time series econometrics is to look at the raw data and understand what is it saying. Now, you can have all the three in single graph, or you can have multiple graphs for them. You must take multiple graph because these three variables have been measured differently. Their scales are different. They are not standardized yet. So you can't take them as it is. So multiple graphs, and you press OK. Once you press OK, you get the graph output. And there are three graphs here. Each of these three clearly shows you there is an upward trend. Each of the three has an upward trend. And it's natural. The loans that banks are giving are rising with time because population is increasing, income of people are increasing. The number of employees should also increase with time because the scale of banks is increasing, and so should the branches because banking is becoming a larger and larger business. The loan books are rising, so the inputs must have risen in order to produce that very high loan amount. So all three are trending, but the trends are quite different, isn't it? In case of output, the first one, top one, you can see that there is a smooth trend from the fourth year till the last year, last second year. But before that and after that, there are breaks in the series. So still you can fit a straight line out of them. It should not be strictly a straight line, but if you fit a straight line, a rough linear trend is visible. That's not the case with labor. Number of employees working in the entire banking sector in India. For initial few years, it remained largely stagnant and then started rising here. And in case of capital, also it increased, but then from 2014 onwards, it started falling down. And why is there a fall in the number of branches? Digitalization. Banks are able to provide a lot of services to customers without having to open physical branches. So this is the idea. You get a feel that yes, all three variables are not non-stationary. You can't use them as they are in the ARMA models or ARIMA or ARMAX models, and you need to accept that they are non-stationary in nature. Again, we go to option view and go to spreadsheet. We have actual data in front of us. What we want to do now is we will close this. Why we will close this? I'll show you. Suppose if you have opened these three variables as a group, or two variables, or five variables, or 10 variables. Now, if you go to option view, in the view option, you will have last fourth option, unit root test in EViews. Unit root tests are your non-stationary tests. If you press unit root test, and if you look at the option test type, in the option view, unit root test, option test type, you will have absolutely different kinds of unit root test. The Fisher ADF, Fisher PP, IM Pearson Shin, Brighton, Levin Lean Chu, Hadri method. Now, we have not discussed about this. Why? Because they check for unit root in the group of variables together instead of individually. But for ARMA model or ARMAX model or RIMA modeling, we need to ensure that each variable is stationary in itself, not together, but in itself. So we need to close this particular spreadsheet and open the variable that we are interested in, output for example, which is our y variable. Output is a y variable, output variable, y variable or dependent variable. Once you open that, you can go to the option view, go to the option unit root test. Now you have your traditional well-known unit root test examples. You can see there's NG parent also, which we have not taken up. Otherwise, most of them I showed you what they are, what their null hypothesis is, what their alternative is. So the most popular ones are ADF, Phillips parent, and the KPSS test. Why are they popular? Because with most of the kind of commercial, accounting, finance, managerial, and economic data, these three tests are able to handle those kind of data well. Sometimes you may have data which is very different, has some structural break, some other issues. In that case, then these unit root tests will not be reliable. Let's say there is a structural break in your data. And then there is also unit root. So it's possible that there are structural breaks in your data and it shows data as non-stationary. But if you remove the structural breaks or break the data as per the structural break into 2 or 3 parts, each of that part may be stationary in nature. So there are tests such as Zivot-Induced test that I have used, or the biparent test that I have used in my PhD thesis, where I tested for non-stationarity along with a structural break. And then you can either locate a structural break and specify it, or you can let the algorithm software decide, looking at the data, where the structural breaks are. You can have one structural break test, or you can have multiple structural breaks along with unit root. Those are more advanced versions. You can read about them. Contact me if you are dealing with such kind of data. But generally, ADF, Phillips parent, and KPSS should suffice. So let's look up the example of ADF. Others you can test for yourselves. Now we have here option of test for unit root in. So in what form do you want to use your y variable or whichever variable? It's not y. You may have 3, 4, 5 variables. Okay, so you may be having Armax or Arimax model where you have one y but multiple x. So whatever variable you are dealing with, do you want to test for unit root in the variable raw data? You want to test it in first difference or second difference? Never jump directly to first or second difference. Always check for the level form data. Okay, always check for the level form data. And then on the right side, you have the option of lag length. How much should be the lag? What generally we do is we let EViews have its default setting. But when you have yearly data, for example, one lag is also more than enough. You may go up to 2 or 3 lags just to feel safe about it. Okay, what are we going to do with this? AR1 model is going to be estimated, right? What is unit root? The beta 1, that is the relation between GDP in 25 and GDP in 24, that AR1 regression coefficient, that should not be equal to 1. It should be less than 1. Okay, so that's what we are going to test. Whichever test you use, the idea behind each of these tests is this: how they estimated, how they executed statistically is different. What assumptions they make is different. So how much lag should be there? 1 lag, 2 lag, finally. So you are allowing maximum 4 lags, but you can't have 4 lags altogether. Any 1 lag is to be taken fine. So how will EViews decide? It will use an automatic selection criterion, which are known as information criteria. AIC, BIC, SIC, or a combined index of them. These are information criteria. They are methods in which you can look at how much data you have and then penalize that data for whatever calculations you are doing, and then you choose a lag which gives the least penalty. So don't get into this right now. You read about it. I'll share you good reading stuff. Read about it. But let SIC be there. You can also focus on AIC, a very popular way of doing it. But yeah, if you EViews is using SIC by default, let it be there. But these choices are very important. They can change the results. Now, the last one is, what do you want to include in the test equation? Only the intercept. So in your AR1 model, you will have only the intercept, or you want to have in AR1 model a trend also, or you want to have nothing, no intercept or trend, simply AR1 model and the error. So which one should be used? Practically speaking, if you don't understand anything, if you understand this, great. Suppose if you suspect that there is trend in your data, stochastic or deterministic, but there is a trend in your data, you can use both trend and intercept and check. But if you suspect there is no trend in your data is not largely trending, then you may ignore trend and only focus on intercept. Generally, don't go for the none option. And ideally, you should report results both with intercept and trend and intercept to be safe in ADF particularly. So that will give your results lot of strength and backing. So we are only using the simplest form, intercept. Even though we know that the variables are trending, we are only using the option of intercept, and we press OK. Once you press OK, EViews will return you a output window. The regression, the AR1 model that it is estimated is given here. We don't need to bother about it right now. What we want to look at is this one, the ADF test statistic. The value of the test statistic, which is based on a t distribution, is minus 0.83. But the critical values at 1%, 5%, 10%, all three are larger than or smaller than, because there are minus numbers, they are smaller than this. So if you look at the probability or p-value, it is larger than 0.05, the standard number that we have. Any probability value, significance value greater than 0.05 means we cannot reject the null. If it is 0.05 or less than 0.05, we can reject the null. It is far higher than 0.05, it is 0.78. So you can definitely not reject the null. What is the null? It is given on the top. That output variable, your y variable, has a unit root. Output variable has a unit root. Okay, and the probability says you cannot reject the null, 0.78. It is far higher than 0.05. So you can't reject the null, and you need to allow accept that this variable is not stationary, in its level form. Now what you can do is you can go to the option view, unit root, and then now we can choose the option trend and intercept both. Okay, trend and intercept, press OK. And if you see the results, still it is not stationary. Still it is not stationary. Now this is the practical question first that I had raised, that if you have a non-stationary variable and if you put a trend in that variable, will it take care of the non-stationarity? No, because when we say non-stationary, we have a stochastic trend. So here we have included this trend variable. You can see that, you can see that trend variable here, and it is significant. So that's a good thing. It's a significant trend, linear trend. But this trend can only take care of the linear straight line trend. What about the randomness around that straight line? Its stochasticity, that cannot be taken into account. So even after controlling for trend, the variable is still not stationary, clearly indicating that you need to deal with the trend in some way or other. You need to make it stationary for sure. Okay, then we go to the option unit root, and now we do the same test. Okay, but with intercept, not trend, because we don't expect first difference to have a trend. It may have it, but we don't expect it. Then we go to the first difference option. We want to check unit root in the first difference with only intercept option. We press OK. And now if you see the test statistic and the probability, it is lesser than 0.05. So now you can reject the null, that output. Which output? D output, first difference of output, has a unit root, is rejected. So the first difference of output does not have unit root as per this test. You can conclude that if you use first difference, you can be safe and you can go ahead and do your ARMA modeling with your output variable. Okay, so your output variable in first difference is the correct way of using, instead of using it directly as it is. So fine, so we have come till here. You can also check other tests in unit root. You can go for, let's say, Phillips parent test. Do not change this thing. Spectral estimation method, for example, let it be default, and bandwidth example also let it be default. Do not change them as far as possible unless you have studied their properties. Let the default option be there, and you can use Phillips parent in level as well as in first difference and then check the result. Let's do it directly in the first difference. And in the first difference, the null hypothesis is there is a unit root in first difference of output. There is a unit root, but as per the test statistic and the probability, it is rejected. So there is no unit root. So both ADF test and Phillips parent clearly state that the output variable, your y variable in first difference, does not have a unit root. So it is stationary in first difference. So your ARMA modeling, ARIMA modeling should be done with first difference. Now, because you have to do one differencing, there is one differencing required to make output stationary. You have ARIMA model where I is 1. So you have ARIMA model where I value integrated of order 1. So you have to do one difference to make that y variable stationary. So now what we do is we go to the spreadsheet and we have the option proc. You can also directly go there here, and here you can choose both output and C. Okay, both output and C, and you can choose, let's say, output and just a moment, labor. Okay, you can do output and labor. You can also do it directly with proc and generate by equation. But the problem with that is it will take a little time and make it tricky for you. You can take any two variables and then open them as a group, as an equation. So once you open them as an equation, that editor window comes in EViews 8. Now that's not a problem in EViews 10 and above, even 9, I guess. So in EViews 8, you do this, a window is opened. See, in the window, in the method option, it is saying least square, non-linear least square, as well as ARMA. So it allows for ARMA modeling also. So how do you do that? In ARMA model, what you need to do is you need to first write your y variable. Okay, your y variable is D output. Why D output? Because it is only in first difference that it is stationary. If you look D2, it will make it second difference. We don't need to do that. If it is stationary in first difference, go with first difference. Organize us 5-10 minutes more and then I will be ending. Okay, so just 5-10 minutes more. So you have D output. You write at the first space, you write C, which is your constant term. All right, and now you need to introduce the AR and MA specification. So you need to introduce whether you should have AR1 model or ARMA1 model. How to determine that I'll show you shortly, but let's assume generally in time series literature, AR1 and MA1 is the most popular option that we generally use. That much lag is required to create an ARMA. Okay, let's assume AR1 and MA1 is the correct lag length, that PQ11 is the correct one. So you can write AR into bracket 1 space MA into bracket 1. And your time period is from 2000 to 2021. Entire data that you have is being used. So the first argument is your y variable, then your constant, then AR1 means AR1 of what? Of that y variable D output, MA1 of the y variable D output, and then you press OK. Okay, then you press OK, and your ARIMA, ARIMA model is in front of you. Why? Because AR1 is there, so you are linking output in today with output last year, output this year with output last year, and then you are also linking output this year with the error made last year. So it's and you have difference output variable one time. So integration is of order 1. So you have ARIMA model where AR order is 1, I order is 1, and MA order is 1. And now if you look at the results, it's very easy. It's basically OLS estimation but with AR and MA structure. Look at the AR coefficient. The AR coefficient is negative. Okay, the AR1 coefficient is negative, and it should be negative because now we have made the variable stationary. Even after making it stationary, if AR1 is 1, it's negative, that is fine. But if it's 1 or greater than 1, then there is some abnormal problem in your data. You need to handle that. There might be some outliers or something. Look at the probability. It is less than 0.05. It is definitely significant. So the null hypothesis that this minus 0.612 might actually be 0. Only by chance it is minus 0.61 is rejected. It is minus 0.61. Statistically significant evidence is there. So there is an AR mechanism, auto regression mechanism, where higher values in the past are resulting into lower values right now. But mind you, where we are talking about change in output, not output level, change in output. So outputs is the change in output is it slows down with time. Earlier the change in output was very high, so change in loans from one year to another was quite high. With time it is falling down. That is what this AR1 negative sign indicates. Look at the MA1, it is positive but less than 1, so invertibility condition is satisfied here, and the coefficient is also statistically significant at 0.05. It is significant even at 1% level, and it's a positive value but less than 1, so invertibility is fulfilled, but it's quite high, it's not very small. So there is good amount of impact of past information, last year's error, on the current output. So, and then you look at the R square of this. Of course the F statistic must be looked at. F statistic, what does the F statistic show? It shows the overall significance of the model. All this AR, MA and the C, all this put together, is your model really significant? Together is your regression model, ARIMA model, able to explain your Y properly? So the F is very small, 1.52, and its probability is also much higher than 0.05. So the model, while individually AR and MA are significant, together is not enough. So this is an indication for you that you should use ARIMAX model, that is introduce some X's also. Your data requires some additional X variables because your AR and MA components are not sufficient enough, strong enough to explain your output variable. That is the first difference of output variable. You need to introduce some additional X also. So from here, if your F is not significant, R is quite small, 0.15, it's time maybe you look at ARIMAX models where you introduce some additional X's. Your R square will improve, perhaps your F statistic will also improve. So a lot of trial and error is required. You can't really have fixed method and fixed step and then take fixed variables and then plug in dumb magic and you will have a wonderful ARIMA model. So this is one indication that maybe you need to look for ARIMAX model. What can we do with this output? The important thing that we need to do is impulse response functions. Okay, while this ARIMA model is not very good, look at the F statistic, which is low. Otherwise AR and MA components are fine, but we can go to the option view and then look at the option ARMA structure. Once you do that, it gives you a lot of options like the roots, So if the roots are within the circle, see if the roots are within the characteristic polynomial, like they are in the circle, it's a stable stationary process. Okay, so stationarity condition for the estimation is fulfilled. But what we are interested in is impulse response function. So view ARMA structure, this impulse response is given here. Now, how long do you want to go? It's basically forecasting. How long do you want to go? So if I create a shock or change in that E term in ARMA model, that E term is there. In every ARMA equation, finally at the end, E term will be there. Okay, current error term. If I change that error term by 1 standard or 2 standard deviation or one standard deviation, if I change that, okay, by 1 unit or 1 standard deviation, what will be the effect on Y, which is my output variable, loans variable, over next 24 years? If I allow 24 years time, by what time will it subside and die down? You can, instead of 24, you can have 12 also, 12 years. So yearly data, so whatever you specify a number will represent that frequency of data. If it's monthly data, then this 12 will represent 12 months. If it's yearly data, it will represent 12 years. So let us take a 12 years example, and we choose the option graph. And what is the impulse? That is, what is the shock we are introducing? EViews allows you to use a standard shock, which is 1 standard deviation in the error term. What is the shock? Some abrupt change in banking sector. RBI announces some new policy and nobody knew about it, and that's a shock, correct? That can be shock. Or you can specify a specific shock. Instead of 1 standard deviation, it can be 1.5, 0.5, 2. Don't go for that. Go for 1 standard deviation. Okay. That's a standard thing in time series literature and in time series research. Then you press the option OK. Once you press the option OK, you see 2 kinds of impulse responses: actual impulse response and accumulated one. What is this blue line here on the top figure? What is this blue line? This blue line shows the change in your output variable, Y variable, if there is a 1 unit shock in error term, 1 standard deviation shock. Where did this shock come from? It came from, it can come from RBI's announcements, government's policies, or India banking sector faces some new challenge, some new quantum computing or AI technology is launched, and it creates a whole surprise for the whole banking sector. Those are shocks here. They can be anything. So a 1 unit shock in the system, in your ARMA model equation, what will happen to your output variable, loan variable? It's not actually loan, it's change in loan. So what will happen to change in loan? It will be high initially. It will react very harshly. It will be quite high. You can see the value is quite high initially. Blue line is quite high, and then it falls. Okay, goes much lower in negative territory. Again bounces up, goes down, and then fades away. So it takes, if you look at this impulse response function, it takes around 6 years for it to subside, a 1 unit shock. What is accumulated response? It is cumulative response. So shock, 1 unit shock in first year is the effect in the first year. In the second year, it is effect in first year plus effect in second year. In the third year, it is effect in first year plus effect in second year plus effect in third year on the Y variable. That is accumulated shock. And if you look at the accumulated shock, which is the much better way of analyzing it, again, it goes around 4 or 5 periods. So it takes around 4 or 5 years for a 1 unit shock to die down in the output variable, in the loan variable. So India's banking sector takes 4 to 5 years to absorb a 1 unit shock in the banking sector, such as a new RBI announcement, new policy, new technological change, fintech adoption, etc. It can be anything. Now, the problem with this impulse responses are that E is a pure error, white noise term. We can't link that E to Y variable, or if you are using Aremax, where various X are also there, you can't link that E to any specific, that shock to any specific X variable or the past value of Y itself. That's the problem with ARMA. So that is why we go for structural VARs or structural VAR, where you can identify the shock and link it to a specific X or Y variable. So we can pinpoint, because of change in this would happen in system. Here it's a pure composite shock to everything, the whole system. Which X, which Y, lag of Y, we don't know. It's just a shock. Okay. So this is what you can do. Finally, you can go to view and you can go for residual diagnostics, where you can check for serial correlation, that is autocorrelation test. You can also go for heteroscedasticity test. You can also go for correlogram Q test statistics. These are all diagnostic tests. You read more about it. I'll share you very good reference materials. Stability diagnosis are for the structural breaks in data. Are there any structural break in your ARIMA model? Maybe in the year 2010. So for example, I go to stability diagnostics, and the most popular test for structural break is Chow test. But in Chow test, you should know which year the break has occurred. So I press Chow test and I enter the mid value between 2000 and 2021. The mid value is 2010. I add that. So what I'm saying is there a structural break in 2010 in how the ARIMA model is behaving? Is there a shift in the ARIMA model itself? Okay, I press OK, and a result comes. The main statistic is this F statistic. Null is that there is no break. What does null mean? The null hypothesis that we are testing is there is no break. It is smooth. The ARIMA model that you have estimated acts same from 2000 to 2010 and from 2010 to 2021. It is the same. That's the null hypothesis. F statistic significance is quite high at 0.02. It is far lower than 0.05. So you can reject the null. So what it says in year 2010, there is a fundamental change in your ARIMA model. Perhaps you should treat 2000 to 2010 as one period and 2010 to 21 as another period and run ARIMA separately for them. This is very simple analysis. Don't judge based on this. I'm giving an indication. What does the Chow test say? If you've done it well, if you've studied everything well, if Chow test says that specific year there is a break, maybe you should either incorporate a new dummy variable to account for that break, or which I'm sure the next trainer will teach you, or you can then check for you can then, if your period is very long, monthly or quarterly data of last 20, 30, 40 years, then you can break it into 2 or 3 parts, howsoever many breaks are there, and then estimate ARIMA for each of them separately. All right, so I think with this, we should end our session. And I'll just again, yeah, one thing that I'd like to share with you is my contact details as per the PPT that I have specifically included. So you can have it here. There were a lot of, I have covered, yeah. These are my contact details. You can take a screenshot of it. So yeah, organizers and host madam, I have completed my session. You can take over now. And those who want my contact details can just take a screenshot of this and get in touch with me.
Thank you so much, sir. So, dear doctor, on the behalf of organizing team and all the participant of our 7-day online workshop on research methodology and econometrics, I extend our heartfelt thanks to you for your insightful and engaging session on time series econometrics. Your expertise, clarity of thought, and depth of knowledge you shared have provided our participants with the strong foundations and sparked meaningful academic curiosity. The way you explain complex concept with such simplicity and real world relevance truly enrich the learning experience for everyone involved. So we deeply appreciate the time, effort, and dedication you put into preparing and delivering the session. Your contribution has made a significant impact, and we are truly grateful for your support in making this workshop a success. So we hope you all the privilege from you again in the future. Thank you so much, sir. Thank you. Thank you.
Thank you so much. So we'll end the session. Anybody who wants to get in touch with me. Take care and bye bye. And Dr. Malik, I'll take your leave now, sir.
Yeah, 1 minute, please.
Yeah.
Thank you very much. I request all the participants if they can open their camera for group photo.
Yeah, that is.
And Dr. Bhagirath, you are requested to close the screen.
Should I close my screen? Should I?
Yeah, you can. No, you can. I mean, you can stop sharing now.
Okay,
Have
I'll
a group
stop.
photo.
Yeah.
Yeah. So all dear participants, if you can open the camera, I am waiting for you all. So meanwhile, I would also, thank you, Dr. Bhagirath, for his insightful, session. It was very, detailed. The way you have, covered all time series concept, and it was, too much easy to follow up with you. and the concepts were quite clear. So I appreciate your efforts and your time. Always you are ready to serve J&K Economic Association. So I am very thankful on my own for giving us your precious time. And it was one of the lengthiest session, but participants have shown the great interest by staying active. So their
Thank you, Dr. Malik.
participants.
Thank you. Thank you so much. Always a pleasure working with you.
I'm glad. So dear participants, I am going to capture your photo, but most of the people are not there. So let me hide non-video participants to have a good photo. So be ready, I am capturing the photo. And again, I want to request you, I have uploaded the previous sessions on our YouTube. So at least you can like, subscribe our channel and share with your friends all the workshops. So I think this is our 4th workshop. All the workshops are freely there available. So you can take advantage of that. You can practice yourself again and again. And Dr. Bhagirath is one of the rich resource persons we can connect. I'm going to tag him on LinkedIn in our posts. Most of the resource persons I'm tagging. So feel free to reach them. But also, follow our pages on LinkedIn, Facebook, and this. So thank you very much. So we are now, closing the session.
Thank you. Good night. Good night.